All right, so we'll come now to the real part of this is analyzing the model predictions. This is one of the things some of our younger engineers struggle with. There's a very important difference between modeling and analysis. Modeling is I build a model and I generate predictions. That can be done by the computer. Analysis is the interpretation of those predictions to infer, discover weaknesses, insufficiencies, strengths in a design. The computer can't do that. It can't tell you that this is a good design, this is a bad design. That's up to you as a thermal analyst. So, a good thermal analyst does more than just generate the predictions. They look at the data, they understand the design, they investigate the heat flows, they truly understand the physics and make sure that the simulation is behaving as the physics of the problem dictates. So, don't think that as a thermal analyst, your job is to generate predictions and hand it off to somebody else to understand. Your job is to understand what those predictions are telling you. So, to this end, there's verifying the results. Make sure that everything matches physics. One of the important things is, before you run an analysis, what did you expect it to do? You should not push the button to say go without any idea of what you expect. If I sized a radiator, I expect that radiator size to have given me temperatures within some range. So, never go into it just saying, okay, I'm going to run a prediction and see what it is. Really think through before you run, what should I get out of this? Because that's the only way you can see whether anything makes sense or not. So, we talked earlier about model correlation. That's a measure of how accurately the model predicts the actual measured values under the same conditions as you test. It does happen much later in the program because it takes a while before you get to a point where you actually have the hardware. Doing what you can to configure your model to handle as many different cases is beneficial. You want to be able to produce the critical results that you need without the need to spend quite as much effort upfront post-processing. So if you know what you're interested in from your model, the data products that you want, you can make sure you tailor the output to give you that. There are some post-processing tools out there, but knowing what you want before you run it lets you set it up, put it into an easy format, makes it easy to interpret. So setting up the tools to be able to post-process what you want is very useful. First thing you check when you run a model is temperatures. Contour plots are good for that. If you suddenly see something that goes from 100 Kelvin to 200 Kelvin over a small distance, well, something looks wrong there. You want smooth gradients between things. You don't want sharp discontinuities. What's supposed to be cold is what's supposed to be hot. You want to look and see, are there any places where the local max and min values are causing you issues. So you can do that XY plots. So over time, so yeah, it might look great here, but you know what? When I looked at this, there was a sharp spike and it went up and then came back down again. Well, what happened there? Is there maybe some sun glint? Did something get in here that caused a really high temperature? So you might not be able to see that from a single contour plot. You might need to either animate it or look at temperatures over time. Look at the mins versus the maxes. For heaters, for us, we have something called gold rules. We basically want to make sure that we aren't using too much heater power because there are the unknown unknowns out there, and so we want to keep our heater duty cycle under 70%. The duty cycle is defined as the amount of power that I expect to need divided by the available power. So I always want to have 30% reserves there. Thermal Desktop has some good things for post-processing. They do the XY plotting. We showed some of that. Their contour plots. They've got the animated contour plots. And then they do have some methods for querying the maxes and mins, writing output text files, calculating sink temperatures and heat flows past the solution or post-solution. So whenever something doesn't look as you would expect it to, first place to look is the heat flows. So is the heat flowing from where you dissipate it to where it's being rejected? Is it picking up too much along the way? Is it dropping off too much along the way? Is it going where you expect it to? Do you need better isolation? Do you need better conductivity? The heat flows really, understanding the heat flows is far more important than just producing the temperatures. You're excellent thermal engineer when you understand where the heat's going throughout your design. So always strive to understand that and then be able to communicate it. When somebody asks you, well, why is this doing this? Well, because, the heat went from here to here. This is what's causing us to be hot. I think somebody once said that temperatures are the footsteps left behind from heat flow. And I thought that was an insightful way to put it. So here are some typical data ways that you might look at things. This is a contour plot, so I can see what my temperature ranges are, what's cold. Here's a heater power table, so over different cases, how much heater power was used. Here's a XY plot of time versus temperature. This was a launch analysis, so we turned on some things and we launched. Some things got hotter, some things got cooler. So you get to see what the temperature evolution over time looks like. Tabular data, this is definitely an eye chart, but it does show you, okay, here are all my components, here are the temperatures over various cases, compare them against my temperature requirements, highlight anything that looks like it doesn't have sufficient margin. Alternately, there's another way that you could look at this, and that's what we call a graphical table, where I put the range of temperatures over a number of cases, and then see how that looks inside of my yellow or operational limits, and furthermore inside of my survival limits. So, am I doing what I should be? Am I centered happily and have the margins? And then lastly, the heat flow diagrams. Where is heat being dissipated? Where is it flowing? Is it going from where it's dissipated to where it's supposed to be rejected, as you would expect? We talked earlier about an equivalent sink temperature. This is a good byproduct that can be derived out of the thermal analysis. So what a sink temperature is suppose I've got this surface. It's got some radiation out to space. It's got some radiation out to these other three surfaces, T1, T2, T3. It's got some loading coming from the sun, and then some from the planet and the albedo. Well, this whole environment for this surface can be broken down and re-represented as a single view to a single temperature. And this would be how I would probably want to emulate it in flight. So in front of my radiator, I want to put in a panel that has a temperature that represents the equivalent scene that it sees in flight. And so if you go through and do all the math, it's basically the rad K times the temperature to the fourth of the surface in the field of view, add to that all the environmental backloading, and then divide that by the sum of the rad Ks, and that's equal to the sink temperature to the fourth. So sometimes you may have to further degrade the sink temperature. This is making an assumption that the emissivity that you would have here is 1. It's fully absorptive, but we all know that you're not going to get a cryo panel all the way up to 1. So you might have to have a slightly colder sink for the fact that you don't have a full absorption at this cryo panel here. So post-processing steps, figure out what you need to produce. Are you looking for temperature versus limit tables, looking for heater power tables, temperature and time versus, or temperature, heat versus time? You're looking for contour plots, looking for heat flow diagrams, you're looking for backloads or equivalent sink temperatures. Based on what your data products are that you're to be reporting up to your stakeholders, you then determine what you need from the output file. Do I need temperatures? Pretty much always. I don't know that I've ever run a thermal model and not output temperatures. Do I need the nodal heat loads applied? Pretty often. I'm interested in that. Do I need conductors? Maybe. Capacitances? Probably less frequently. Registers? Maybe I need those for heater processing. Maybe the heat loads would be sufficient. Do I need environmental loads? Am I trying to see, is my sun shield doing its job and preventing solar from getting through? Do I need radiation couplings? Particularly, do I want to see what all the ones are to space? Using a text editor or Cygwin. Cygwin is a Unix emulation shell. Can be a good way to say, give me all the rad Ks that are connected to this particular node or this group of nodes, or give me all the rad Ks to space from this particular set of nodes. Do I need this everywhere? Are there specific ranges that I want this for? Maybe I'm only interested in the heat loads for the avionics. Can I ignore the MLI nodes? That's a place where I could say, hey, you know what? Everything that's 100,000 or 200,000 that's MLI, don't really care about it. So let me just output the things that aren't that. figure out if you can average together groups of nodes or collect them. Got these 30 nodes that represent this component. Well, let me sum all those heat loads up, but let me do an average temperature for it so I can get what the component is. And then figure out, hand calcs. What can you do on the back of an envelope to see, does my design make sense? Radiator heat flows to space. View factor computations and rad case sums, are they close to unity? You'd like to make sure that the rad case sum is close to the area times the emissivity. That should be, times the sum of all the view factors equal to 1. Do you have heat flow requirements across critical interfaces? From this box to this base plate, I'm only allowed to dump 2 watts. I'm supposed to be isolated and handle my own. So what is that doing? And the overall system energy balance, is what's going in flowing where it's supposed to? Is it going out where it's supposed to? This can be at an overall system energy balance or, at a component level energy balance. So this is a tool that we developed at Goddard using the OpenTD API. It basically looks through the concap file and identifies from the comments in the different sections what are all the heat loads, what are all the heaters, what are all the PID controllers. It then takes that and figures out what logic it needs to add to the CINDA file before it runs to output relevant information. So for the heat loads, I want to know what's the power at each time step. I also would like to know what's the average temperature of the nodes to where that power is applied. Heaters, I want to know what's the on-off point, what's the available power, what's the heater power at a particular time step or at each time step. PID controllers, what's the process variable, what's the control variable. And so that logic gets written, and what it does is every time step it outputs this to the output file, and then we post-process that output file and bring that into Excel, and that's kind of our quick look thing. So I get all of my heat loads, I get all the data at every time step, so I can now plot what the heater's doing. I never have to worry about missing a time step. I can get duty cycles out of it. I can rack and stack what the power summary is. I can reorganize things such that I know that this component or this sub-element, this instrument is this much heater power and this much survival heater power and this much dissipation, this much PID heat. So that's an example of what can be done with the API. Essentially what we're doing is intercepting the process to execute the model and saying, let me insert this extra step. So you've generated this EC file, but before you move on to solving it, let me add this extra logic in so that I get the data out that I want. So the OpenTD API was introduced a while ago, but it really is an incredibly powerful capability to allow you to change the behavior of Thermal Desktop, get in and get to data from it, automate repetitive tasks, and really do a lot more than you could do without it. So in this case, we went through some examples of post-processing the sample model problem. These were the temperature requirements that were given to us. So these were some example things to be able to bring in some of the user files, manipulate it into Excel, figure out the minimum, figure out the maximum, and this basically would just go through and give you some examples of how to create some of the workbooks, which would then be able to look and see over all my cases, what's my min, over all my cases, what's my max. And so we would look here and see, okay, these look pretty cold. These look pretty cold too, particularly compared to E here. This one is a little too hot. Down here I had some that were too cold. So suggests that maybe I need some operational heaters to see what's going on. These were way out of where we wanted them to be. You can see some of them are well colder, some of them are well hotter. Certainly some problems there. So when we evaluated those, we figured out we needed to do some things differently. So this all came from the user logic TBL files. We did go an alternate method where we said, let's just go and use the Thermal Desktop capabilities to gather that information out of the save files. So we would go through here, the post-processing, find the results, min-max task. and that would give us very similar information. So here, much like the table with the user logic to output, there's a slightly different syntax, but you can specify what information you're interested in pulling out of the save file and export it to a CSV file, which can then be brought back into Excel. So here we went through similar exercises and found that, okay, there were some differences. Basically, what we found was that there was a min being found in a hot case. When I did it first manually, I was only looking at cold cases under the assumption that that's where I would have it. So, when we got all of them, we basically got the same behavior out of it. So these are some of the hand checks that we can do. So when we look through everything, the hot beta 75 produced most of the hot predicts. We ran that to make sure that it was good and set the output to all for the save file. So once we had everything in there, now we could look at the heat flows rather than just temperatures or Qs. So the heat flows can be done. You can try to do it through the QFlow from results, but sometimes it's easier to just use the model browser. And from that, you can say, give me the heat flows between submodels, and you could say, I want it between this submodel and all of them, or just between these two. So we were looking at deck 1 and global from everything. So basically, where's all the heat going from deck 1? That was the avionics deck with all the boxes mounted to it. So we looked at that and said, okay, well, what's the orbit average power, for everything? And that gave us about 243 watts of dissipation going into it. Adding 114 watts from component C gave us 357 watts total. So I've got my component C conducting into the sidewalls, coming up, going into the deck, all of my avionics. That total was 357 watts. How much was going out? 378. All right, we're in the right neighborhood. Seems to be reasonable, within 6%, not bad. I'm going to get some solar loading that's going to leak through MLI and get in there. Another sanity check we did was, what are the rad Ks between deck 1, all the non-MLI nodes on deck 1, and space. So that produced a rad K sum of 1,560 inches squared. When we compared that to 0.89, which was the emissivity, times pi times the radius squared, and then subtracted off that center portion, that gave us an effective view factor of about 76% for the radiator. All right, want my radiator to have a pretty decent view to space, 75, 80%, pretty good. And we looked and said, okay, well, let's assume that the deck is one temperature. If I take that 3.66 e to the minus 11 sigma, multiplied by 1560 for the rad K sum here, average temperature of the deck of 11 C, converted to K, 371 watts radiated to space. Well, right in line with my 378. So sanity check. Seems reasonable. Nothing seems really far out here. Model seems to be behaving as far as physics is concerned. We went through and did some contour plots on component N. We saw there was some very large gradients. So it turns out that some of these heaters had really high heat and temperatures on it. They would spike up here, when the heater came on. Well, this was very thin and titanium. Not a big surprise that that was bad. So we ended up adding a bunch of aluminum tape over it to help smooth out the gradients. We relocated the heaters in some areas. We increased the conductivity around the sides so that it wasn't quite so isolated in order to try and bring that temperature down a little. Also noticed that the assumption that the heat could just be applied around this perimeter was probably not the best assumption. This component ran considerably hotter up here than it should. Well, realistically, these things are base plate mounted, so the heat isn't going to uniformly be distributed around this. So adding in a surface here that can then conduct to this perimeter allowed us to better model what was the behavior there. So a poor choice in modeling here. Improve it by representing the base plate and then the conduction to the base plate, because I'm certainly going to want to conduct easier to the cold area than I'm going to want to conduct to the hot area that's got to fight its way all the way back down here. So, yes, this would be one temperature, but the heat flow is not going to be uniform around the outside. So we went through, made some updates to things. Here's where we added in the effect of the tape. So here's where you can see a density multiplier for adding in some tape, added in a U and a V conductivity improvement, so that made it so that the tape effects were modeled in there. We also took a look at the heater power usage, so you can post-process the heaters, and you can figure out exactly which things you wish to output from here. One of the ones that they do give you is duty cycle, which is handy to have. So when we processed that, looked at the outputs, this looks considerably better now with our things. But we did notice that there was some strange behavior in just the hot beta 75 case. So why is that one bad and all the rest okay? Well, turns out that shrinking this a little bit too much, hot beta 75, well, there's a small gap there. When we got in there, there's some sun, so that was heating things up. So we increased the radius to close out that gap a little bit better, and then we got things behaving much better because we weren't getting this solar illumination on the outside of component N. Cold exceedances, well, how do you solve a cold problem? You add a heater. So we added some extra heaters to this deck, put in the sizes, and lo and behold, here's some of the duty cycles, a little higher than we'd like, increased some of the sizes, and then came up with what those sizes need to be. So here we have everything within its limits. We have the heaters sized appropriately to give me sufficient duty cycle on things, and we handed off our results to the systems engineer who asked us for it. He thanked us and begged us to come work the project when they win the proposal. So to close everything out, every thermal analysis should begin with expected performance. How do you determine whether your results are reasonable if you don't know what to expect? The analysis of the model predictions is the responsibility of the thermal engineer. Your job is not just to generate predictions, it's to analyze the data that you have. Trust the results after you've done some basic verifications with hand calcs and first principles. And trust your judgment. If something doesn't look right, look a little deeper under the surface, figure out what's going on. Anticipate the data you're going to need from the model. Very often you only need a small fraction of the overall model to produce the data products that are going to be asked for. Automating that post-processing can take a little bit of upfront time, but if you have to do it over and over and over again, that setup will really help you because you'll be able to more efficiently bring the data in and look at the results. Very often, you may fix one thing and you break something else. So there's often unintended consequences. Solve one problem and another problem pops up. So make sure you understand why it's doing it. That's part of your job, to understand the behavior of the system and figure out what's going on. If something unexpected occurs due to a model update, you brought something in and now all of a sudden it's broken, understand why that is. Is it something that is physics or is it a modeling error? So anytime you make a change from the status quo of where everything was working and now it isn't working, there's always the possibility that you introduced an error. So dig deep to understand whether it's an error from the model or whether it's really a problem with the design. And learn to separate requirements that are not being met due to the design from requirements that are not being met due to modeling practices. So there's a difference. I modeled this and it didn't meet requirements. Well, I modeled it poorly. That's why it didn't meet requirements. Or I modeled it properly and it didn't meet requirements, therefore I need to change my design. So learn to identify mistakes and problems in how you've approached something, how you've modeled it, and separate out what's a design problem from what's a modeling issue. All right, so to wrap it all up, thermal analysis is a cost-efficient way for us to use computer simulations to explore design space, verify that things meet requirements. Much cheaper than build and test, build and test, build and test. Most spacecraft analyses use the geometry model to compute the radiative exchange and the environments, feeds into a thermal network model that predicts the temperatures and heater powers. We've got a pretty solid process for building that and verifying the inputs prior to execution. Certainly helps to understand what the code's doing behind the scenes. Not required, but it's certainly helpful to understand what the algorithms are doing if you ever need to troubleshoot to see why it's not doing what you expect. It's your job as an engineer to make sure that the predictions are reasonable based on the physics of the solution and synthesize those predicts from the model into useful data products for the stakeholders. And physics is physics. If your model's telling you something that doesn't make sense, check the physics. If the design does not or cannot meet requirements, laws of physics must still apply. Yeah, you'd like it to be under 40 C, but you haven't given me enough space for a radiator. I can't do it. I can't bend physics to do things that are impossible. So always make sure you understand the physics and the constraints of the resources that you have, and be able to explain that to the stakeholders that they either need to relax requirements, give you more resources to be able to do the job. But physics is physics. You can't make physics bend to your will if the constraints are such. So, all right, so last slide. I really hope that this is the beginning of dialogues. I don't wish for this to be a one-time thing. My intention, when all's said and done and I get back to the US and we're all settled back in, is I'd like to really kind of have an office hours once a month, maybe twice a month if it's really needed to start off, for an hour and a half. We'll hold it in the evening time, my time, which is middle of the day for you guys. And come bring your questions, and I'll do the best I can to answer them. Consider Professor Peabody's office hours. Furthermore, there's a workshop called the Thermal and Fluid Analysis Workshop. It's hosted every year by a different NASA center, rotates through. This year, Goddard Space Flight Center is the one who is going to be hosting it. It is a no registration cost, so really it's just the costs for hotels and costs for meals and travel, but at least it's a free workshop. It features paper sessions, it has vendor training and demonstrations, and then topical short courses. There might be a course on how to build MLI or how to model this or how to deal with stop analyses or things like that. So it's all focused on thermal and fluids. You're all invited to attend. I'd certainly love to see some faces again there. And if you're interested, the website is tfos.nasa.gov. It's right now in its infancy. We're just getting started with it, so I'm not sure exactly when it is. It tends to be mid to late August before school starts back up. It's almost always after ISIS, for those of you who know that conference. But definitely a different feel than ISIS. It's more of a focus on the analysis and the tools rather than just paper presentations. And then lastly, after I had some chats with Colmore and Ring and told them about this, they thought it was great. If you ever have questions, contact them. They're very friendly, they're very nice, they're very helpful. Support@crtech.com. And Cindy Beer, gave me a direct quote. Please tell them if they ever want to do online meetings with us, we're always happy to do that. So if I haven't answered your questions sufficiently, the experts are an email or a phone call away. And they're, you're paying for support. You're paying for the ability to ask them questions. So take advantage of that. They're great people to work with. They're very helpful. So I would encourage you to take advantage of those opportunities. So.